class. We were working on defining the Lebesgue integral. And the reason we need a Lebesgue integral is because the Riemann integral is not good enough. And we started by defining step functions, which were functions that look like steps. That's why they're called step functions. And we're building up from there. I think you should kind of think about this. If you've ever gone camping and there's that moment where you're making a fire and it sucks, and you're like, this is brutal. We got these like twigs and they are not lighting on fire, and we are trying hard to make these twigs light on fire. And then you're like, okay, we got a twig to light on fire, great. But you have to have faith that we are going to get to like a big rip-roaring fire in like a few lectures, okay? So right now we're playing with these like little twigs, which are these step functions that are only on intervals can they have different values, and they go up and down. And we are proving like all sorts of dopey things about them. Things like if you add them up, then you add up the integrals. And here's a silly one that looks dumb. If the functions go to 0, their integrals should go to 0, but it requires a lot of proof. Okay, so here we go. We're going to prove it. And I think we were in the middle of this proof. Let me draw a cartoon to refresh you on how this was going. So we had a sequence of step functions, fn, and the fn's are going down to 0 monotonically. So they are always decreasing. I call this weakly decreasing. They're shrinking down to 0. And they can never go up again, which is important for us. And in that situation, if they're all going down to 0, and they're decreasing down to 0, then the limit of the integrals will be 0. And we had this set up, which I drew a dopey cartoon over here. Let me draw it again, where we are. So as a recap, we had these functions. So we had, let's pretend we're on some interval, say 0 to 1, which is my favorite interval. And our functions they're step functions, so they should be, if I was going to draw them correctly, I would draw stuff like this. But let's pretend that I can at least draw curvy lines. So they're going down to 0. Here's f1, and then f2 is below f1, and is even more close to 0, and f3 is below f2, and so on. So they shrink down to 0. And we had these sets A, and the sets A were getting bigger and bigger, and they were where f is below some threshold. So we made some line here, which was epsilon naught over 2, and we were looking at when do the functions go underneath it. So in my picture, A1 is some tiny set in the middle here. This is where A1 is where F1 is less than epsilon naught over 2. It's just in the very middle. And then A2 is a bigger set. Let's draw that in. I should fix the colors here. Well, let's get a new color. I think we can do that on a computer. Let's do green. Oh, that's a nice color. Okay, A2 is where F2 is less than epsilon naught over 2. And that's a bigger set. So F2 going from here to there. That's A2. It's a bigger set. A2 all the way from here to here. And then A3 is even bigger. A3 is even bigger. That's this one. From here to there. A3. A3. Okay. And that's where F3 is less than epsilon naught by 2. Okay. So the functions f are going down to 0, and that means the sets A are getting bigger and bigger and bigger. The functions f are step functions, which means they are constant on various intervals. And that means the sets A can be written as finite combinations of intervals, right? So the functions f, they are the sum of these characteristic functions or the indicator functions of various intervals. And so the sets A have to be unions of these like sets that make up the set f. And they are getting bigger and bigger. In probability language, you would sometimes write this. You would write an up arrow to 0, 1. And that means the sets an are getting bigger and bigger. And they are eventually, in the limit as n goes to infinity, every single point will be covered. And that's because every function f is going down to 0. Eventually, you're less than epsilon naught over 2 at every single x. So that was where we left off, essentially. There was one other ingredient, which was we just defined bn to be the difference of the an. So we said bn is an divided by an minus 1 divided by an minus 1. So it's the difference is how much you get bigger. So like here is b2 is this little set, right? b2 is how much you go. I guess it's b3. B3 is going from A2 to A3. That is B3 is that little difference. And because the ANs were a finite union of intervals, Bn is also a finite union of intervals. Finite union of intervals, just like the ands, and not because the ands are expanding to cover all of 0, 1 as n goes to infinity, the bn's, their union covers all of 0, 1. So the union from n equals 1 to infinity of bn is the entire domain of the functions. In this case, I'm pretending it's 0, 1. I think in the textbook they just say some interval. Maybe they say ab, but we'll just pretend it's 0, 1. And the bn's are disjoint. So by the way they're constructed, and that little dot means disjoint. And that is our setup. Okay. Questions or comments about the setup from last time? I know it's a long time in analysis land to go away from a proof like this for more than a minute. So maybe you don't remember anything. That's okay. Questions, comments? Yeah?
Can the bn be empty?
Some of the bn's can be empty, yeah. Like it could be that fn plus 1 equals fn. Empty is okay, yeah.
Right.
So the things they're disjoint, no two of them have any overlap, and together they cover all of 0, 1, the infinite intersection. Okay. Okay, so I'll give you the idea of the proof. We're going to finish it off in a second, but I'll tell you the idea. Because the bn's cover everything, we know that the sum of the lengths of the bn's must eventually be small. And that is because we proved a lemma, like I called the annoying lemma, that if you have a bunch of intervals that cover 0, 1, then the sum of the lengths of the intervals is 1, right? We proved that last time. So we're going to use that lemma, and we know that the sum of the lengths of the bn is finite, and that means eventually the lengths of the bn get very small. So what we're going to do is we're going to corral in our function. We're going to just wait till the bn's have a really small width. Like the sum of all the bn's is going to be less than some epsilon naught by 2 over here. And if we wait long enough that the things are less than epsilon naught over 2, then the functions f, they have to all be below epsilon naught over 2, right? If bn is less than epsilon naught over 2 in size, then the functions have to entirely live for almost the entire interval of 0, 1 in that orange zone where the height of the function is small. So we kind of have two regions where we're controlling the function. The orange region is a very wide region, almost the full domain, 0, 1. But the functions are small there. We know the functions are going to be bounded by epsilon naught over 2 in that orange region. So no problem, that's fine. In the green region, the function could potentially be very tall, but the width of the region is so small that the contribution of the function will be small. And so we're going to combine these two facts to prove that the function, when it's trapped in the green region and the orange region, has to be less than epsilon naught over 2, which will contradict our statement that the integral of the functions is bigger than epsilon naught. That's the idea. Okay, here we go. Let's do it formally. And I need one more ingredient, which is I'm going to let m be the maximum over x of the absolute value of f of x. Actually, I'll just do f1 of x, and that'll be good enough. And I don't need an absolute value. So the functions are positive. They're shrinking down to 0. They're positive. And m will be the maximum value of f1. It's a step function. It only takes on finitely many values. You take the maximum. This is larger than fn of x, or larger than or equal to, for all n and for all x. And the reason is the functions are decreasing, so f2 is below f1, f3 is below f1, all the functions are below f1. So this m is like the highest possible value you could possibly be, and I can add that to my cartoon. You have some height m over here, and that will control the maximum possible height. And then what I'm going to do is I'm actually going to make this region less than epsilon naught over 2m. So I'm going to take this line. So since the union dot of n going from 1 to infinity of bn equals 0, 1, and bn are finite unions of intervals, therefore, the sum from n equals 1 to infinity of the absolute value of bn, where absolute value of a set of a finite union of intervals means the length of the intervals. Let's say union of intervals equals total length of intervals. Some people would call this the measure. We could also write that, the measure of bn if you wanted. And the measure in general is quite complicated, but the measure for intervals is what we've been doing. You take the right endpoint minus the left endpoint. So right endpoint minus left endpoint. Okay, and you sum it over all the intervals. So hopefully that makes sense. In the textbook, they avoid this kind of thing. They just say, like, let Bn equal this union, and they write everything out. So they introduce a lot more notation. I think it's more clear this way, even though you need to know this idea of the length of an interval. That's really what we're doing. So the length of the intervals is equal to 1 minus 0. That's by the annoying lemma. By annoying lemma. Which was finite, what did I call that? Countable additivity for intervals. Countable additivity for intervals. Okay. Okay. So I've kind of thrown a bunch of stuff. I'm trying to say a simple idea, but it's coming out annoying in the notation. Let me know if something is unclear. Does it make sense? Yeah.
Can you just go over what you wrote on the right hand side?
This?
Like
or this one?
Just that whole side would be.
Yes. Okay. So this says when I write. So what does it mean when I say line and I put some set in the middle, like line Bn? Bn is not a number. You can't take its absolute value. What I mean is if you have a union of intervals and you take the line of it, you do the total length of the intervals,
okay.
Where the total length means right endpoint minus left endpoint.
Okay.
And so if you have like 5 intervals, you add it up 5 times the total length. So like any reasonable person would look at this set and be like, how long is the set? That's what they would say.
Okay.
Yes, and it's important they're intervals. If it's a complicated set, then it's hard to say what is the length of the set. But if it's a finite union of intervals, there's like 4 things, add them up, you do that. Yeah, okay. Yeah, great question. Other questions or comments? Okay, so the sum of the bn's is 1, and if it's an infinite series that adds up to a finite number, the tails are less than epsilon. So let's find an n naught so that the sum from n bigger than n naught, so the tail of the set of the lengths of the bn's, we're going to make it less than epsilon naught divided by 2. And actually, I want it to be less than epsilon naught divided by 2m. 2m. So the length of all the bn's, all put together, all infinitely many of them, as long as you look at n naught and higher, is very small, less than epsilon naught over 2m. And in my picture, that's really saying exactly over here that everything past here will be less than epsilon naught over 2m. And so the height of the functions are going to be bounded by m. The width will be bounded by epsilon naught over 2m. So the total contribution will be less than epsilon naught over 2. You're going to see that in 1 second. Okay. And so now I'm going to look at the function f of n naught of x. The function f of n naught of x. F of n naught of x, it has 2 parts. It has the part where it is bigger than epsilon naught over 2 and the part where it's smaller than epsilon naught over 2. So this is equal to, I'm going to write it like this, f of n naught of x times the indicator that f of n naught of x is bigger than epsilon naught over 2 and where it's smaller. Okay, and as a little cartoon, let me do a little cartoon of just this one function. I know I had more than one function in the other one. This one has just one function, f of n naught, which is some silly looking function like that. Okay, and it's got 2 parts. It's got the part where you're here, below epsilon naught over 2, and it's got the part where you're above, right? So there's this bit on the outside, that's where you're above, plus this bit where you're below. Okay, great. This set has a name. The set where you're less than epsilon naught over 2, we call that an. This is an. This is really the set an. So where you're less than epsilon naught over 2, this was an naught. That's the middle bit. What is the set where you're bigger than epsilon naught over 2? That is everything except a naught. Everything except a naught. That is 0, 1 minus, or take away an naught. So this bit here is an naught, and everything else is the complement. Okay. And because of the way we define the b's, this set, everything except minus a and naught, also has another nice name. This happens to be exactly equal to the sum, and by the sum I mean the union n greater than n naught of bn. So the bn's are what you get by doing a and naught plus 1, take away a and naught plus 2, take away a and naught. We know that altogether they cover 0, 1. So if you take everything and you subtract to the middle bit a and naught, you get just all the things that are bigger than n naught. And this is very nice because this annoying set, so this set in yellow, we know it's teeny tiny. We know it is less than, it's not too big. So I'm going to do a bound here. I'm going to control the height of the function here. I'm going to say this thing is less than m. And over here, the function is less than epsilon naught over 2. So there's two parts. There's the part where the function is potentially big. That's going to be on a small set. And there's the function where the function is small. That's going to be on a large set. Yeah?
Is the union of bn the left side plus the
That's right.
right side?
It's the left side plus the right side in my picture. In general, there's no reason for it to be exactly on the left and on the right. That's how I drew my cartoon. So in general, it could be like, somewhere, some collection of intervals somewhere in 0, 1, and it's just all the places where the function is like that. So this is like a common thing that happens in probability or in this kind of analysis. You have the function and you divide up into two parts. You say where the function is potentially bad, but that's a small set, and where the function is controlled, well, that's a big set. And we're going to go from there. So I'm going to say fn of x, it's exactly equal to that, and these things by inequalities are less than or equal to m times the indicator of the union n greater than n naught of bn plus epsilon naught over 2. I could write the indicator of the set a and naught, but I'm just going to write 1. There's just like always less than epsilon naught over 2 in this region. So like you're either in the set or not. In any case, you're always less than or equal to 1. So that'll help me a little bit. Is the inequality clear? I'm trying to explain in, it's not clear. Okay.
I don't think so, no.
Okay, so let's see. There's really 4 parts, okay? Let's highlight them. This one is that. The yellow one is this. The yellow one is an equality. So the yellow one, I didn't do any inequality. That one really is the same. Fn naught is less than m because m was the maximum height of f1, and Fn naught is less than f1. So that is bounding the height of the function. So the function can potentially go up, down, but it's going to be less than m. No matter what. Is the green and the yellow okay? Okay, great. And then on the other side, it's the same kind of situation. This one is bounded by epsilon naught over 2 because you must be in the set where we're less than epsilon naught over 2. So that's why you're less than epsilon naught over 2. And then I bounded this entire set. I just said the indicator of anything is less than 1. All right. Yeah?
What does the first one mean?
The first, which one?
Before the curly bracket.
Okay, yeah. Let me remind you. This was a notation I think I introduced last time that 1 curly bracket any set S is the function which is 1 if x is in S and 0 if x is not in S. Yes, without knowing what this is a terribly confusing thing. I guess I need of x somewhere, of x. Yeah. Okay, and I guess I'm using it a little bit wishy-washy. This one should say 1 indicator fn naught of x. There should be like x such that this, and then it should be of x, but like hopefully you get it. Yeah.
Can you go over the picture again?
Yes, let's go over the picture. So actually, now that I have the terms color-coded, let me color-code the picture of this thing. Okay, let's do this. This is great. So we have the middle set is the orange set. That's a and naught. And in a and naught, the whole function is less than epsilon naught over 2. That was the definition of a and naught. That's the orange term. Then there's two things. There's the height over here, which is bounded by m, because m is the absolute tallest anything could ever be. That's in green. So I'm saying the function is less than m because the function is less than m everywhere. Right? M is like a global height restriction on the function. And then the yellow is exactly the width of these little pieces over here. The yellow is the union of n greater than n naught of b n, which is everything except for the set a and naught in the middle. This is very good. Yeah, great questions, guys. Okay. And now this is the whole point, is that this is the indicator function of a union. That is, it's a union of intervals, right? Everything here is an interval because the functions fn were step functions. So this indicator function is itself actually a step function. And what is the integral of this step function? It's precisely the sum of the lengths of the bn's, because that's the definition of the integral of a step function. So we have this function fn naught was some weirdo, like step function, could be like totally crazy, but we have bounded it by a very nice looking step function that we can control. It's m times this step function. This step function is always height 1, plus epsilon naught over 2. And not only that, we know the length, the total length of the intervals of the step function, because that's how we chose n naught. So we're going to be in good business here. So therefore, the integral of fn naught is less than or equal to what? We proved integrals for step functions obey inequalities. It's less than m times the integral of this guy. Let me write it out as one more step. N greater than n naught of bn plus epsilon naught over 2. And I'm integrating from 0 to 1. So this is 1. Okay. Yeah, so I did it on the interval 0, 1. If you were going to do it on the interval 0 to 7, you would have to pick like an epsilon naught over 2 times 7. But I did everything on 0, 1, so that works. So I just took my inequality and I integrated it. And then there's one last step, which is to write down what this is. M times the sum of n greater than n naught. And then you have the length of the intervals, bn, plus epsilon naught over 2. And this is less than or equal to m times epsilon naught over 2m plus epsilon naught over 2 by choice of n naught. Okay? And so therefore, the whole thing is less than epsilon naught. Okay. So the function, its integral is less than epsilon naught. We've trapped the function, so that way we can make sure its integral is small. That's the end of the proof. Okay, so this kind of trapping theme, you're going to see more and more complicated versions as we go. This is like the simplest version. There's eventually a theorem called the Lebesgue dominated convergence theorem, which is a very famous theorem. In the Lebesgue dominated convergence theorem, there's a function called the dominating function. And the dominating function is going to like trap the function f and prove that its integral is converging in the way you want. In this thing, our dominating function was the function this times this plus that. Okay. All right. Okay. I think we have a couple corollaries. Oh yeah, okay. So here is my, this one I made up because it's going to be something that's coming up later. I'm going to call this the monotone convergence theorem for step functions. Monotone, that's the monotone. Okay, monotone convergence theorem for step functions. So in this one, we are proving if you're going down to 0, in the monotone convergence theorem for step functions, you're going up to a function f. So let fn be step functions, and I'm going to write fn of x up arrow to f of x. That means converging to f monotonely. Converging, and I'm going to say weakly increasing. The textbook writes non-decreasing, which I do not understand what it means. There's too many double negatives for my brain. Weakly increasing. It can't be going down, okay? And I'm going to assume f is a step function too. Is a step func. Okay. So you have a bunch of step functions. They're going up to some other step function. Then the integral of fn converges to the integral of f. Okay. That's the monotone convergence theorem for step functions. The proof is a one-liner with what we've already done. You let gn equal f minus fn, and then gn down arrow to 0. So the fn's are going up to f. If you let gn be the difference, f minus fn, then the gn's are going down to 0. The gn's satisfy exactly the statement of the theorem before. So therefore, by the theorem, the integral of gn goes to 0, which means the integral of f minus fn goes to 0, and you can move the integral over. F equals, I'll write it like this. Fn goes to f. Okay. Why am I telling you this theorem? This is like some obvious restatement of the theorem. Later in the course, we're going to have the monotone convergence theorem for any function. And the exact same statement will hold, but with the leading is a step function. So it'll work for any function. Yeah.
So what do you mean by the lead increasing?
Yeah, I mean,
Can't go down.
can't go down.
So it can go flat.
It can be flat.
Okay.
Yeah. So f1 could equal f2, but you can never go down. Yeah, that's right. Yes. Yeah. So and once again, the textbook calls this non-decreasing. So it's like flat is not decreasing,
Sure. Yeah.
but I like weakly increasing. Yeah. Yeah.
In the last line, should there be an integral on f?
Yes, there should be. Yes, thank you. Very good. Okay. I was testing you. Okay. All right. Yeah. So I'm showing you this monotone convergence theorem is like one of the famous results. There's a section coming up called famous integrability theorems or something like that. And this is one of them. We'll see it. There's this one and there's the Lebesgue dominated convergence theorem. Those are the two good ones. Okay. Here is another corollary that we're going to need later. Corollary, this one is straight from the textbook, 2.2.7, and it's used in some proofs coming up. Fn are weakly increasing. Step functions. Step funcs. And the limit as n goes to infinity of fn is greater than or equal to 0. So before I said the limit is some function f, now I'm just saying the limit is something that's bigger than 0. Like they get bigger than 0. Then the limit as n goes to infinity of the integral of fn is bigger than 0 too. So before they were converging to something, and the limit of the integrals was the integral of the something, but now they're just like always bigger than 0. The limit will also be bigger than 0. We're going to use this one later. The proof is like silly and doesn't have any like content to it. You just like take the thing and like you just like play with the 0 in the right way. So I'm going to leave the proof. If you want to see it, go read the textbook. See textbook if you want. Okay. There's some trick with like gn is the maximum of fn 0 or something like that. Okay. Okay. And now we are ready. The reason this is exciting, well, I'll stop for questions because we're about to start another thing. So this is like our crappy twigs are about to become like less crappy twigs. We're going to use our crappy twigs to light the good twigs on fire. That's what we're doing now. Okay, so we're into the next section of the book called the Lebesgue Integral. So everything up until now has been step functions, and now we're doing the Lebesgue Integral. You know, I've always wondered, what is a bègue? Because like in French, le means the, so Lebesgue should be the bègue, but what is a bègue? I'll never know. Okay. And we're doing definition 3.1, 2.3.1. So we're on to section 2.3, which is, so far we've been doing only step functions, but now I'm going to tell you what it means for any function to be Lebesgue integrable. A real valued function is Lebesgue integrable. Real valued function f is Lebesgue integrable. Lebesgue integrable if, here are the three things you need. The first thing doesn't have a label. The other things are called A and B. There is a sequence of step functions. A sequence fn of step functions, step funcs, such that two conditions hold. A, the sum of the n equals 1 to infinity of the integral of the absolute value of fn is less than infinity. So the step functions are sort of absolutely summable in integral. That's a nice thing. And B, of course, the original function f you were talking about better be related to this function f. These fn, f of x, is equal to the sum n equals 1 to infinity of fn of x. So we make the sequence of functions fn, and they're all step functions. This is important. The function f can be any old function doing all sorts of things. The fn's have to be step functions. They have to be defined on intervals. And f can be written as the sum of the fn's. There is one last condition that is really tricky and technical, which is that this only needs to be true not for every value of x, but only when it makes sense. Whenever sum n equals 1 to infinity of fn is less than infinity. So when this sum is infinite, there is no relationship between f of x and the sum. F could be any value. All right. So this is what it means for a function to be Lebesgue integrable. It means that there is a sequence of functions, of step functions, which we know, and those converge to the function there. When this happens, we say, we say it's tilde equals the sum of fn. So this notation is going to come up a lot in the next little bit. This tilde equals notation. Oh, and maybe they do it with one. Okay, I think they only do it with one equal sign, like that. All right. And when that happens, we say that the integral of f is equal to the sum of the integrals of the fn's, summing from 1 to infinity. I guess this can also go from 1 to infinity. So there you go. If you want to know what the integral of a function is, you write that function as an infinite sum of step functions. You know how to do the integral of a step function. You add those up. That's the integral of a function. Fantastic definition. Okay. Questions or comments about this definition? Yeah.
Is the this and when this happens, is that when the sum is less than infinity?
Right. This is all part of part B. Does that answer your question?
So when you're saying when this happens, you're saying A and B hold?
Yes, right. When all of this stuff happens and A and B hold, then we say F. Yeah. Okay. This definition, very nice, is extremely vague and like non-constructive, right? If I gave you an actual function and I was like, please find the integral of the function x squared, this is like useless, right? Like we got to come up with a sequence of infinite step functions. There is one other major issue with this thing. Not only is it like not useful practically, but there's one other. If you see, whenever you see a definition like this, we say the integral of f is this. You should be worried. Does anyone think of what is the problem with this kind of definition? Oh yeah, that's true. The infinity is taken care of by this thing. So the sum of the fn's, their integrals will always be finite. So this thing can't be infinity. That's not the problem. Yeah?
We're saying the integral is another integral?
Yeah, we're saying the integral is another integral, but we know the integral of these ones because they're step functions. So this one we know how to do. It's the b minus a thing. That one's okay. So we can calculate for a given f1, f2, f3, we can calculate the right-hand side. So that's not the issue either. Yeah?
Is it like the integral with respect to what? Or are we just assuming x?
Yes, it's always, the integral sign always deals with that. Yeah, that's true. It's always with respect to x. Did you have an idea? Okay. Yeah.
Is it that we don't know what the f's are?
You mean the f1? This is fundamentally the issue, right? So I'm thinking of a function f, and I would like the integral of f to be a number that makes sense, right? And you're telling me first I gotta go out into the wild and like find the sequence of, I gotta cook up the sequence f1, f2, f3, and then I add those up, and that's the definition? Like, what if I go find a sequence over there, you run into the corner and you find like a different sequence over there? Who is to say that we both get the same answer at the end, right? So this definition really makes it seem like it depends on the sequence f1, f2, f3. So this is like, there's a lot of definitions in math that are like this, that are really non-constructive, and you should ask yourself, is this even a definition? Like, for this thing to be real, for the integral of a function to be defined, it needs to have the property that it only depends on the function, not on some crazy sequence of functions that you like cook up, right? So question, does the integral of f depend on the choice of f1, f2, ... right? the way I have heard this is an aphorism coined by my dad, who is also a well-known mathematician from Romania. He says, if my cousin in Romania comes up with a sequence F1, F2, F3, will we get the same answer? I don't know why he has to be in Romania. He could just be over there. Anyway, okay. So that's a great, anytime you see a definition like this, you should say, does it make sense? The way mathematicians say this is they say, is it well defined? Is it well defined? And well defined means, like, can you find the integral of f? And that makes sense as a single number. How do we know it's not actually multiple numbers? Then it wouldn't be well defined. Okay. And we're going to answer this question because there's a lemma coming up that says, here is what we're going to go towards, which is corollary 2.3.3, which says, I can zoom back in one. Okay. If f is like the sum of the fn's, and f is like the sum of the gn's, so if you and your cousin in Romania come up with a sequence, you come up with a sequence f, your cousin in Romania comes up with a sequence g, then the sum of the integrals of the fn's equals the sum of the integral of the gn's, summed from 1 to infinity. So once we prove this corollary, then we'll know it's well defined, because it means no matter which step functions you find, they always have the same sum, and that sum is the thing we call the integral of f. So this requires proof, because without it, you don't know. And the way we're going to prove it is we're going to first prove a lemma. This will be a corollary to the lemma. We're going to first prove lemma 2.3.2, which is like the corollary, but only for inequality. It says if f is related to some functions, fn, and f of x is greater than 0, so if you have this sum of functions and it's always bigger than 0, then the integral, the sum of the integrals is bigger than 0. Okay, so that's the lemma we're going to prove. Okay, and we're about to prove it, but this is a good place to stop. Any questions about why we're doing this? You'll see once we prove this. This is basically proving that it's going to be greater than 0. We're going to prove these two things are equal by proving the difference is both greater than 0 and less than 0 by using the lemma. You'll see that in a sec. But questions about why we're doing what we're doing? Okay, let's jump into it. And again, we're going to use heavily bullet points A and B. Bullet points A and B are the only thing that we have to work with, so that's what we're going to use. So we know, we're told f is like the sum of the fn's, and so we have bullet points A and B. And what we're going to do is we're going to argue like this. Since the sum of n greater than n naught of the integral of the absolute value of fn, not this, the sum over all of them, is less than infinity, that is point A. Therefore, for any epsilon greater than 0, find n naught so that the sum n greater than n naught of the integral of the absolute value of fn is less than epsilon. That's how we're going to start. So by point A, this thing is summable. Eventually, the tail is less than epsilon. Okay, now we're going to make a new sequence. Consider the sequence Gn, defined as follows. So, like very roughly speaking, the sequence Fn, everything past n naught doesn't matter. It's so small, it might as well not be there. Like f is fundamentally the sum f1 to fn naught, and all the stuff after that is like a little bit of tiny dust sprinkled on top. And so we're going to like really make that kind of concrete by making the sequence G that is really like f itself. So Gn is going to be the core part of f, which is f1 plus dot 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 all the way up to fn naught, plus, and then we're going to add on all the annoying bits. The worst case scenario for the annoying bits, which is the absolute value of fn naught plus 1, plus the absolute value of fn naught plus 2, plus dot dot dot, plus absolute value of fn naught plus n. So there's n terms here at the end that we add on. So in the worst case, the integral of all these things is going to be less than epsilon. That's how we chose n naught. everything at the end there, all this stuff is so tiny. You should think of this stuff as like almost meaningless. And that's Gn. Okay. This sequence, why did we do this? Why did we take these absolute values? Because when you take the absolute values, now the GNs are weakly increasing. GNs, by definition, GNs are weakly increasing. And so by the lemma we had before, the limit of the GNs, oh yeah, I'll say and the limit of the GNs is greater than 0. Why is it greater than 0? Oh, yeah, okay. The limit of the GNs is greater than f, which is greater than 0. And that's because f of x greater than 0. It was one of the hypotheses. Let's see. Yeah, f greater than 0. Yeah, okay. So the GNs are these weakly increasing sequence of functions that eventually their limit is positive. And so by the corollary that we just did, by corollary 2.2.7, we know that the limit of the integrals of G is greater than 0. So this was the thing we just proved before in our like monotone convergence theorem for step functions. Okay, and it's all good here because the fn's themselves are step functions, right? So we're still in step function land. Everything is a step function. That's why we're able to operate like this. Okay, and when the limit of the g's is bigger than 0, you're going to see what this means. So here's the big chain of inequalities. 0 is less than the limit as n goes to infinity of the integral of gn. But gn is two parts. It has a part where you sum up from k equals 1 to n naught of fk. That's like the main part, this main part, okay? And then there's the part where you sum up starting at n naught. So you go k equals n naught plus 1 to infinity of the absolute value of fk. All right. And there's integral signs everywhere. I want the integrals of the g. So the integral of this is an integral of finitely many terms. You can move the integral sign inside. And this one is an integral like this.
Would the second one be as it goes to n?
Yeah, you're right. Yes, it should. That I was also okay. Very good. Yes, also a finite sum. You go to n, you take the limit. Thank you. Very good. Okay. Remember, I said this is essentially f, right? This blue part is essentially f, and that's going to prove that f is greater than or equal to 0. But let's or close to 0. But we got to do a little bit of finagling. I'm just going to add on one more thing to make it super crystal clear. I'm going to add on something in the middle. This is a common math trick. Integral of fk. I'm going to add on. What am I going to add on? This infinite sum. N equals n naught plus 1 to infinity. Actually, I don't want it to infinity. I just want it to n. Okay, great. And I'm going to add fn plus the absolute value of fn. That's what I'm going to add on. Okay. Okay, yeah, all right. Look, I'm writing something silly here. This part doesn't depend on n at all. There's no n's here. Okay, so the limit might as well move to over here. The limit as n goes to infinity. Okay, great. And then I can just delete this and put that over here. The limit as n goes to infinity. This is to n naught. Okay.
So is it supposed to be k equal to n naught plus 1 and then fk?
Yeah, so I've just added on a term, and I gotta copy and paste this thing over here. Let's do that. Okay, plus, and then starting at n naught plus 1 to n of absolute value of fk in an integral. Okay. And
Sorry, in the middle one, are those h's then? Because is it saying n, like start at n and then go to n?
it's a k. Yes, thank you. Yeah, that's what you're saying. Okay, yeah, this should all be k. Very good. K, k. There we go. Okay, now it makes sense. So I've added on this term. Why did I add on this term? I added on this term because on one hand, we're going to have n naught plus 1, n is going to infinity. We're going to have everything we're missing over here. So we're going to have everything we're missing over here. This thing stops at a naught. This thing covers me all the rest of the way with that fk. And then we're going to tack on all this stuff. That's just another copy of this. This is the same integral twice, the absolute value of fk. So by adding on this term was non-negative. That's why I could add it on. F plus its absolute value is always greater than 0. Like f plus its absolute value is equal to 0 if f is negative, and it's twice the absolute value if f is positive. We're adding that on. That was totally legit. And now I can split it up into two parts. So, but this is equal, and we're going to have the limit as n goes to infinity. And now we have the sum, k equals 1 to n of the integral of fk. And that was by combining this and this together. Those combined to give that. Right? So we had 1 to n naught, and then we had n naught plus 1 to n. This is going 1 to n. Okay. Plus, we'll have the limit as n goes to infinity. We have the other parts, which are the absolute value parts. And this one is the same thing twice. This is twice the sum, k equals n naught plus 1 to n, and the integral of fk. So the GNs were kind of defined in this clever way to sort of like have the essence of n and like a little bit of error left over. And then I added on even more error just to make the absolute values like they get seem nice and make this guy appear and make this thing appear. Because this limit by b, by point, or I guess by the definition of the integral, by the definition of the integral of f, this is the integral of f, right? When f is like a sum, f1 plus f2 plus f3, the integral of f, the definition is that it's the infinite sum. And that's what we have here. So that's the integral of f. What is this stuff over here? Well, it starts at n naught and it goes all the way up to infinity, but that's less than epsilon. So this thing is less than epsilon. So by that, this whole thing is 2 epsilon. So we have 0 is less than the integral of f plus 2 epsilon. If you rearrange that, we have that the integral of f is greater than negative 2 epsilon. But of course, this worked for any epsilon greater than 0. What numbers are greater than negative 2 epsilon for any for any epsilon? Since epsilon arbitrary, the integral of f is greater than 0, which is what we want. Okay. So a little bit of a fancy thing. I think the essence is this idea of defining the g to be the f's plus a little bit more. And we kind of forced an increasing sequence to appear in our construction. All right. Questions about that one? Yeah?
Where does the epsilon come from the second last step?
Oh, so this whole thing, this sum, is less than the sum from n naught plus 1 to infinity of the integral of fk, right? And n naught was chosen. How was n naught chosen? N naught was chosen so that the sum from n naught to infinity is less than epsilon. Okay. Okay, so what do we have? So we have these inequalities. Now we're going to prove the corollary. The reason we want this corollary is that we're going to use to prove this by doing things two ways. So we're going to prove this now. Can I select it? That would be nice. Let's do that. Oh, okay, I have to be dexterous with my mouse. Okay, let's copy and paste this down below so we can put the proof in. Okay, so if f is the sum of fn's and f is the sum of the gn's, then the sum of the gn's and the sum of the fn's have the same integral. And here is the proof. This is a very simple proof using what we just did. If the sum of the fn's and the sum of the gn's are the same, then we have that 0, which is f minus f is the same as f1 minus g1 plus f2 minus g2 plus ... So the sum of the fn's give f, the sum of the gn's give f, and they're the same. And so if you subtract it from itself, you get f1 minus g1, f2 minus g2, and this will all work out. And you can check a and b if you want, but it's gonna work out. So 0 is f1 minus g1, f2 minus g2. By the lemma, 2.3.2. Lemma 2.3.2 said, if you have a sequence that is bigger than 0, then the integrals are bigger than 0. Well, this is a sequence whose exactly 0, so it's also going to be bigger than 0. By lemma 2.3.2, the integral of f1 minus the integral of g1 plus the integral of f2 minus the integral of g2 plus dot dot dot, this infinite sum will be greater than or equal to 0. Okay. And therefore, the integral of the fn's, when you add them, n equals 1 to infinity, that is bigger than the sum n equals 1 to infinity of the integral of the gn's. So the integral of the fn's is at least as big as the gn's. And that was, again, using the fact that this alternating sum is greater than or equal to 0, because it actually was 0. Okay, but by the same logic, by the same argument, the opposite is true. So just flip the g's and the f's, do it backwards, and you'll get the integral of the gn's is at least as big as the integral of the fn's. Okay. And if one is bigger than the other, and the other is bigger than the first one, then they're equal. That's what we wanted. Therefore, equal. Okay. The theorem about the space L1 that we were trying to get to. Gn, okay. Okay. All right. So questions or comments about any of those proofs? Yeah.
Could you go back to the lemma that we just heard?
Yes, of course. Yeah.
Can you just go over the term that we added, how we combined it in the next line?
Ah, okay, yes. So the term that I added was fk plus the absolute value of fk. And actually, you'll see this quite a lot. So there's this trick that x plus the absolute value of x. It's equal to 2x if x is bigger than 0, and it's 0 if x is less than 0. So this is a common trick to add on something that is positive only. It's like the positive part of x. So that's what we did. And the point is we have an f, and we have all the f's up to n naught are in the first term, and all the f's after n naught are in this term. So if I combine them together, I get all the f's, which is what I wanted. And then what did it cost me? Well, I have a bunch of this garbage of the absolute value of fk's. Like, I don't care about those, but I know they're small.
Okay.
So that was okay to add on. So what I was doing is essentially I had the first n naught terms, which I know is the essence of f. I'm missing a little piece of f. I put on the little extra piece of f, and I'm sure that it's not costing me anything because I know it's a little piece of f. I know it's small. It's less than epsilon.
Okay.
Yeah. Yeah, great question. Okay. So the next theorem is exciting because it is the definition of the space L1. So this is theorem 2.3.4, which says L1 of R, which is the set of Lebesgue integrable functions, equals the set of f such that the integral of f is less than infinity. And this is a vector space. A vector space. And integral is, so the operation of doing an integral, it's called a linear functional. So functional means it maps into R, the integral of a function is a number, and linear means it respects addition and scalar multiplication. Okay, and here is the proof. So what do we have to show? Must show that the integral of f plus the integral of g equals the integral of f plus g, and the integral of lambda times f equals lambda times the integral of f, right? And once you show that, then everything will follow, I believe. How are you going to show that? What does it mean to do the integral of f plus the integral of g? So if you have, for all fg in L1 and lambda in R, well, if f and g are in L1, that means their integral is less than infinity. And if fg are in L1, there must be, so find f n, so f is like the sum of the fn's, and g is like the sum of the gn's. So when you do integral of f plus integral of g, you're actually doing the infinite sum of the integrals of fn, and you're doing the infinite sum of the integrals of the gn. And the claim is that f plus g will be the sum of fn plus gn. Okay, you have to check, if you want to be very technical, you should check A and B, right? You got to check points A, B in the definition of this tilde equals thing. But it's like pretty clear. Okay, and you really should do it with a lambda. If you want to do it with a lambda, I can do it with a lambda as well. Lambda times f will be sim equal to, tilde equal to, I keep calling it sim equal to because that's what you type in LaTeX. Okay, it's the sum of lambda fn. And again, you got to check points A and B, but like they just work and it all works out. So this is the definition that we wanted. Oh, okay, there's one more inequality that we want to prove. Yeah, okay, there's one more. This is technically more part of the theorem. I'll say theorem 2.3.4 continued. And it says that the integral obeys inequalities. So if f is less than g and both are in L1, and so I mean, by this I mean like for every x, g of x for all x, then the integral of f is less than the integral of g. And the way you prove this one is you use one of our lemmas from before. So this one, the proof is g minus f is greater than 0, and that means by lemma 2.3.2 that the integral of g minus f is greater than 0. And that will imply this thing, because we know you can add the integrals from what we did before. Okay. So we know I did skip. Okay, please check. I'll write exercise so you know I skipped it. Exercise. If you want to check, you can check the definition A and B to make sure that these things work. If you have a sequence fn and a sequence gn, you add them together, you get the thing. So the definitions like go through sums and scalar multiples. Okay. And this is exciting because now we have the space L1. All right. Yeah.
So the functions, are they all like real valued?
They're all real valued.
All real valued? And
Yes.
then the integral you're doing, like, is there a difference between saying it's Lebesgue integral or Riemann integral, or are you specifically?
Yes, we're saying Lebesgue integral.
Love.
Yes,
Okay,
yes.
cool.
Everywhere. Sorry, integral f means the Lebesgue integral. Right. Okay. So this seems great. Seems like we were doing good. Yeah.
Scroll down.
Yes, I can scroll it. Yeah. Tell me when to stop.
I think right there's good.
Okay. So it seems like we're on top of the world. We have the integral. But you should still feel kind of disappointed because we have these step functions. Step functions, I understand, those are like really simple. And I said, whatever you can write something as a limit of step functions, it's integrable. But like it's still unclear. Like, is the function y equals x squared, is that integrable or not? Right? Like we still don't know. And the textbook has this like great, this is like as far as math textbook go, this is the juiciest gossip I've ever seen. Let me show you what the textbook says. All right. It's right here. Okay, here we go. Definition 2.3.1. That was our definition. It's fairly simple, although it may be a little disturbing. Okay? This is like math. This is like the hardest a math textbook will ever go. Okay. Condition A does not involve f in any way. Condition A was, remember, that the sum of the absolute values of fn are finite. Okay? The sum of the integrals. Condition B says that f equals the sum of the series at those points where the series converges absolutely. So that's saying that f is equal to the sum of the fn's, but only at these certain points. How big is this set, right? So it could be that the sum of the points, what if the sum of the points where the absolute value is finite is like nothing? Like what if it blows up everywhere, right? So we had this definition. This is what the textbook is saying. Let me scroll back up to the thing. And this is, I think I mentioned it. I was like, this is some subtle stuff. over here, when we had a and b, right? So is this whenever? Whenever this happens. But what if this never happens? Like, what if this is just always infinity? And then this condition is like a nothing condition. Like, I'll just come up with a sequence of fn's whose sum of absolute values is always infinity, and then that will cover every function f, right? And then I have the integral of every function f, right? So this is like a real problem. But look, this is what the book is telling us. The book is telling us about this. Where is the book? I click on this button. Okay. If we can find a sequence of step functions fn satisfying A such that the absolute value diverges at every point, so this is like our evil scheme, right? Let's come up with a sequence of fn that diverges everywhere. Then we could write f is equal to the sum for any function f, okay, inside the interval ab. Since we have proven that the integral is well defined, we know that such a sequence cannot exist. So it's saying, look, if you could do that, then you could have two functions that are not equal, but they would have the same integral. And we proved that you can't do that. So you cannot come up with a sequence of f1s, f2s that do this for some like really subtle reason we don't understand, right? In fact, this series cannot diverge at every point of a non-empty open interval. So this is like a fact about reality. You cannot cook up a sequence f1, f2, f3 that will diverge on a non-empty open interval. And actually, we can prove more. So there's a little proof baked into this paragraph that we're going to do. You can prove that if f equals f1 plus f2 plus dot dot dot, and z is the set of the points where this diverges, then the integral of the characteristic function of z equals 0. So the only way that you can cook up this set that we were like, let's worry about this set. This one. The set where the opposite of where it's next. Where it's infinity, it's saying don't worry about those sets. The integral of those sets is always 0. We can add this as a little remark over here. Remark. The bad set is small. Where small means it has an integral that is 0. And actually, why don't we prove this formally? Let's go down to where we are over here, and we can prove it formally. So this is like the remark proof. Let z be the set of x such that the sum of the absolute value of fn of x diverges. Let's say I'll write equals infinity because they're absolute values, so that tracks. So let f be the sum of the fn's, like tilde equal the sum of the fn's, and let z be the set where it diverges, right? So bullet point B is saying, let me remind you what bullet point B says. B says f of x equals the sum of the fn of x outside of z. So on the set z, you don't have to do anything. You do nothing. But on the set z, or off the set z, which is the bad set, they're equal. Okay. Then the integral of the indicator of z of x equals 0. So in other words, the set z is a small set in that it has an integral whose integral is 0. This is just like the rational numbers. Like the rational numbers are a great example. The rational numbers are so small that when you integrate them, you get 0. This is called a null set. Okay, and actually there was like a proof of this, right? And the proof actually, let me just show you in the textbook because I think they prove it in the little paragraph that comes up. Let's do that. Okay. So here is their proof. Indeed, if g is the characteristic function of z, then f plus g is also equal to the sum. And so the integral of f plus g equals the integral of f. And this implies the integral of g equals 0. Okay, let's write it down. I think this is worth writing down. Okay, so let's do a proof. So f sim equal the sum. I keep calling it sim equals. I'm LaTeXified to the core. Okay, fn, right? This is given. And f plus the indicator function of z is also equal to the sum of n equals 1 to infinity of the fn. and you can say check B, no x applies. So in B it says, the definition was they're equal outside of the set Z, and this function is 0 outside of the set Z. So they're equal. They're still equal. It's a very silly, vacuous thing. And A has nothing to do with the left-hand side. So it's still true. So since, let's say 1 of Z of x equals 0 for x not in Z. Okay. All right. And then we had a theorem that said if you have a function which is equal to the sum, then the integral is just the sum of the integrals. So therefore, the integral of f equals the sum of the integrals of the fn's, and the integral of f plus z is also the sum of the fn's, the integrals of the fn's. And therefore, by adding and subtracting them, right, we just proved that you can add and subtract integrals. Therefore, the integral of 1z is equal to the integral of f plus 1z minus the integral of f, which is 0. Okay, there we go. So the set of points where it diverges, the step functions diverge, is this small set Z. And it's small in that it has an integral which is 0. By the way, if you were in probability land, let me return to probability. I should get a hat that I put on. That would be okay. This says the probability of the set Z, U is in Z, equals 0. There's a 100% chance you are not in the set Z. Right? You pick a point at random, the chances of being in the set Z, 0. Okay. Okay. Let's go back to the textbook. So the set Z must be in some sense a small set. Such a set is called a null set. A null set means it has probability 0, or it has measure, the integral of that set is 0. We can say that the series f, this sum converges to f for all x except a null set. This type of convergence is called convergence. This is the worst thing I've ever seen in my life. Almost everywhere. Right? So when someone says almost everywhere, they mean it converges except for a set which has probability 0. So there's a 100% chance it converges in some sense. Okay? That would be, I think saying a 100% chance would be more accurate than saying almost everywhere. Almost everywhere is a silly way to do it. Okay, we're going to talk about this in section 2.7. All right, and this is the best place ever to end a class. Look at this. At this point, the reader may expect some examples of Lebesgue integral functions. And then the rest of this says, fuck you, I'm not going to do that. We know that we know that every step function is integrable, but that's not a satisfactory example. We would like to see some other examples. And then it's unfortunately, it would be awkward to try to do that. It would be awkward to try to prove that. It would be like trying to evaluate this using Riemann sums. The reader has to be patient and let the theory develop a little bit further. And then we will easily construct some non-trivial examples of integrable functions. Okay, so that's where we are. So we're still building the fire. So it seems like we're done, but we've moved from birch bark to a twig, okay? We're gonna get there.
So they literally say, okay, isn't it you can use, how can we use it? Shut the fuck up.
No, it says you listen. We're barely started. is what it's saying. Yeah, and I will say, okay, this textbook is a little bit unusual. A lot of other textbooks, they start with the Lebesgue measure first. So we're kind of speed running straight into doing the integral. And then if you want to know probabilities, it's you just integrate the function that's 1 on the set. Other people start with the probabilities or the measure, and they have something called simple functions. So instead of step functions, they have simple functions, and they do it that way. So this textbook does it a little bit differently. I like it because you get to integrals sooner, which is what we actually care about. But this is the annoying part. Now we're at some point where we technically know what the integral is, but we have no examples of where it actually works. So we have some theory that potentially could be nothing, but we're going to build up, and we're going to get a bunch of theorems that tell us, oh, if your function is a limit of these other types of functions, then it'll work. So that's what it's saying here at the end. Okay, that's a great place to stop. We're going to pick it up next time with some more stuff about Lebesgue integrals, and that's where we're going. Okay, see you guys next class. Have a good weekend.